So it's 3 p.m. Good afternoon. I hope you had a good lunch break. We start our afternoon session. Bubbles and droplets. Before starting, I would like just to take a few seconds to share my. Okay, I cannot share my screen. No problem. I will just give you the details of the philosophical transactions of the Royal Society A special issue that has just been published, actually at the end of August, so a couple of weeks ago. And you will find the details in the flyer on the website. The Royal Society asked us to give you the details so that you can download the issue and all the papers. And it is the special issue of DSFD2020. So the first speaker of this afternoon is Francesca Mangani from Leone Technical University with the presentation Density and Viscosity Effects on Deformation, Breakage and Coalescence of Large Bubbles in Turbulence. Francesca, you have 15 minutes. At 13 minutes, I will tell you that you have just 2 minutes left. So the floor is yours, please.
Okay, thank you. Can you see my screen?
Yes, we see it very well.
Okay, if there are problems with the connection, please let me know because sometimes it happens. Okay, so thank you for letting me participating to this conference. I'm Francesca Mangani and I'm doing the PhD at the Vienna University of Technology. I work with Professor Alfredo Soldati and with Alessio Roccon, and I will talk about today density and viscosity effects on deformation, breakage, and coalescence of large bubbles in turbulence. The motivation behind our research is that multiphase flows are very common in many natural phenomena and also in industrial applications. For example, in breaking waves, there's the formation of droplets on the top of the wave, but also of bubbles below the surface of the ocean, and this increases the exchange of the carbon dioxide between the ocean and the atmosphere, but also in the atomization of liquid jets in combustion processes, we can observe the breakage of thousands of droplets, and so understanding this phenomena is important to optimize these applications. And also in oil speed mitigation, for example, we have a dispersed phase of oil in water, and we would like to control this phase. So in general, deformation, breakage, and coalescence are very important to be understood in order to understand these phenomena. And multiphase flows are, however, very challenging because they involve a lot of space and time scales. So if we deal with the turbulent flow, we have the largest turbulent scale down to the Kolmogorov scale, but also we are considering some interfacial phenomena that are related to the molecular scales. So we have a range of 9 orders of magnitudes, and we have to choose to choose a smaller range to solve, because the actual high performance computers are able to solve up to 3 or 4 orders of magnitudes. So our approach can be distinguished in this overview of many numerical approaches, and they are categorized based on how many scales are solved and what's the size of the drops or the bubbles. Our approach is belong to the interface resolved simulations. So we solve all the turbulent scales, and we consider drops or bubbles that have a size above the Kolmogorov scale. So we describe the behavior of the interface. And so the interface is described by means of the phase field method that exploits this phase variable that has a constant value inside the dispersed phase and the carrier phase, and it undergoes a smooth transition across the interface. This transition is occurring in a thickness that is related to the Kahn number that we can set in our simulations. And also the thermophysical properties can be expressed in terms of this phi variable, and so also they also follow this function that is a hyperbolic tangent function. So the governing equations are the incompressible Navier-Stokes equation and the Kahn-Hilliard equation that describes the behavior of this phase field. that evolves according to the velocity field and also to the diffusion of the chemical potential that can be written in terms of this energy functional. And we also introduced this correction term in order to deal with some drawbacks of the method. And the term that is responsible for the coupling between the Navier-Stokes equation and the Cagni-Hilliard equation is this one, which takes into account the surface tension forces. And it's written in terms of the Korteweg tensor. So we solved the turbulent flow considering a shear Reynolds of 300 and the following grid. And the phase is initialized with 256 bubbles, so with a volume fraction of 5%. So it looks like this, this picture at the beginning of the simulation, and later the bubbles or droplets can deform, break, and coalesce. So before going to the results, I would like to focus on the parameters that we considered in our simulation. We are interested in the interaction between turbulence and bubbles. And this is driven by the presence of vortical structures, so the presence of velocity gradients that can perturb the surface of the bubble. And these perturbations can be then transferred to the internal flow of the bubble. But there is something in between, that is the surface tension, that can act against this perturbation and tends in general to maintain a spherical shape of the bubble. So the first parameter we consider is the Weber number. That is in fact the ratio between the inertial forces and the surface tension forces. Then if we look to these pictures, we find another interesting aspect. These snapshots are sections of the flow field showing the turbulent kinetic energy, both in the carrier phase and inside the bubbles. And we can see that going from a viscosity ratio between the two phases of 0.01 to a value of 100, the vertical structures inside the bubbles are significantly different. So when we have different properties between the two phases, we have a different local Reynolds number, and the Reynolds number is related to the properties, so to both density and viscosity ratio. So it's reasonable to ask if these two other parameters can can modulate these perturbations of the bubbles. So we sum up, I sum up here the simulations we did, and we consider two Weber numbers, and for each of them we chose different combinations of density and viscosity ratio. The first one is a reference case where both ratios were taken equal to 1. Then there's a group of simulation where just the density ratio was taken different from 1, and analogously for the viscosity. So we look here to the density and the viscosity effect separately, and then we look to them in a combined way. So we choose both ratios different from 1, and so equal to 0.1. So the first results we observed are related to the bubbles topology, and in particular to the breakage and the coalescence phenomena. The breakage happens when there's a ligament arises in a bubble, and then this ligament is stretched, and then it's broken, and then there's the reshaping of the bubble. The coalescence instead happens when two bubbles approach each other, and a film, liquid film is formed between them, and then this film becomes thinner and thinner, and at a certain point it's broken, and the two bubbles become just one, and they reshape again. So the main outcome of these events is the evolution in time of the number of bubbles. And here you can see this evolution for different density ratio and viscosity ratio. So the number decreases and it sets on a stationary value at the end. And we can say that both density and viscosity don't introduce an important effect. This is also confirmed by looking to this qualitative picture that is referred to the steady state of the simulations. And we can observe in this plot in the horizontal direction the density effect. So we increase the density ratio from 0.001 to the reference case of 1. And in the vertical direction, we observe the variation of the viscosity ratio, so from 0.01 to 100. And we can say that in all the pictures, the number of bubbles stays more or less the same. The situation is different, quite different when we increase the Weber number. So not so much for the density, that does not introduce big variations, but for the viscosity, we observe that increasing the viscosity ratio, the number of bubbles decreases. And this is also visible in this qualitative plot. So increasing the density ratio, the number of bubbles is more or less the same. Instead, increasing the viscosity ratio, it's visible that the number of bubbles is decreased. So first of all, the viscosity has an important impact on topology. And secondly, this impact is just visible when the Weber number is increased. So when the surface tension is lower and the bubbles are more deformable. Now I would like to talk about the bubbles morphology. And here you can see a time sequence of the deformation process of a bubble. And at the end of this, let's say on the third bubble, you can see that some ripples and dimples were formed. So some areas where the curvature is high, so these areas are very convex, and also some areas where that are concave, so the curvature is highly negative. And so we decide to describe the formation of the bubbles considering the mean curvature, that can be defined in general as the mean of the two principal curvatures that are respectively the inverse of the two principal radius. And we can also write this the curvature in terms of the field variable. So we computed the probability density function of the curvature considering the surface of all the bubbles for the steady range of the simulation. And we observed that increasing the density ratio, the PDF become larger. So it means that the highly positive curvatures, so the ripples, and the highly negative curvatures, so the dimples, become more probable. So the density makes when the density is increased, the inertia is increased, and so the deformation happen in a stronger way. And for the viscosity, we observe the opposite effect. So when the viscosity is increased, the PDF become narrower. So the highly positive and highly negative curvatures become less probable. We confirm this looking at these pictures, so in this qualitative plot. And this is quite visible looking in the increasing the density ratio, and is even more visible increasing the viscosity ratio, where in fact here you can see that the red areas and the blue areas are not so many, and also the bubbles have a more or less spherical shape. When we increase the Weber number, this effect occurs again and is even stronger. And this can be seen both looking at the probability density functions, but also looking at the qualitative pictures, where we observe, especially for a very low viscosity ratio, the presence of many red and blue areas. So to conclude, we observe that the Weber has a very important impact on topology and deformability. And when this Weber number is increased, the density and the viscosity effects become visible or are enhanced in general. And the viscosity can play a crucial role on topology more than the density, but both density and viscosity influences the deformation, and in particular they have an opposite behavior. So I thank you for your attention, and I'm open for questions.
Thank you very much, Francesca. You were within your first slot of 13 minutes, so we have room for discussion. And thank you very much. Are there any questions from the audience? Okay, Sayed Hosseini has a question. Is the double well potential used for the chemical energy in the CH equation? And if so, why not reality's equation of states?
Yes, the double well potential is used, and this method has a thermodynamical basis, so it comes from the Canillard
equation,
and Canillard studies. So yes, this is how it is used for now for a long time, and it has some drawbacks, but it works well in this form. And so yes, I hope I answered
okay.
to.
Okay, if Sayed has other questions, okay. Simone Colucci asks which computational tool, code, or solver you employed.
We have a Fortran code parallelized with an MPI technique, and we used the pseudospectral method for the DNS, and we in particular the Fourier in the spanwise and in the stringwise direction, we use the Fourier transforms and the Chebyshev transformations in the vertical direction, and yes, there are many other details, but
maybe you can also give them through email. Actually, Professor Wagner from North Dakota State University has the same question that I had. So thank you very much, Alex. What about the Reynolds number for the deformation here? Do you keep Reynolds number fixed? And also, what about the Weber number? You showed us Weber number 1.5 and 3.0. Are there numerical issues related to different values of Weber number? Did you try any larger Weber number? What about the Reynolds number? So these two non-dimensional.
Yes. The Reynolds number is fixed and is defined in terms of the properties of the carrier phase. Yes, the shear Reynolds number. So the density and the viscosity are the one of the carrier phase, and it's fixed, and also the Weber number is fixed and also defined in terms of the properties of the carrier phase. And in the past studies, also lower Weber numbers were used. There are no issues no big issues in increasing it. So in this study,
I would expect a larger values of Weber. For instance, you mentioned at the beginning in spray formation and breakup, you there usually have Weber's numbers in the order of hundreds or thousands. Okay, so this was just a curiosity for myself. If you have ever tried, okay, you should have breakup phenomena, catastrophic breakup phenomena for larger values of Weber, because the effect of surface tension becomes negligible as Weber number increases. Okay. Yes. Have you ever tried, for instance, Weber in the order of 10, 20, 100?
No, we have never tried these values. Here, the focus, in fact, was more the density and the viscosity ratios. So, considering the past studies, we pick two numbers of the Weber that shows significant differences from each other, and fixing these two Weber, we focus more on the effect of the density and the viscosity.
Okay.
But so large Weber were not considered in the past studies.
Okay, Kai-Chi has one quick question because we are out of time. Could you explain intuitively why increasing the density, the curvature increases?
We think that when the density is increased, the inertia, the internal inertia of the bubble is increased, and so it has a higher momentum, and that's why it's more likely to have this this mobility and this the deformation of these ripples and dimples. So we relate the density effect to the inertia of the flow.
Okay, I think that we are unfortunately out of time. Very interesting talk. Congratulations, Francesca.
Thank you.
Francesca, one more time.
Thank you.
And, we have to move to remain tight in our schedule. The next presentation by my colleague, but above all friend, Marcello Sega from Zurich, intrinsic structure and dynamics of moving droplets. Marcello, are you there?
Yes, I'm here. Thank you for the introduction.
Marcello.
I just need to share the screen.
Welcome, my pleasure. Share the screen. Let me see if there is any...
It's still disabled.
Disabled, okay, so I have to make you...
Yeah, now it works.
Okay.
Now it should work.
Yeah, thank you, Claudia.
Yeah. Perfect. Please just confirm that you can see the main window.
Yes, yes, we see it very well. Marcello, please, you have 15 minutes from now. At 13 minutes, I will tell you that you have 2 minutes left.
Excellent. So we basically go at the other end of the spectrum that we saw in the previous talk in terms of scales. We're actually below the nanometer in the sense that we will be interested at resolving what is happening below that scale at the very interface between different phases, liquid, gas, and solid. The tool which I'm using here is basically molecular dynamics, and I think that the slides shows exactly what is the core problem I would like to underline. You see on the right an instantaneous snapshot of a molecular dynamic simulations of a liquid droplet, and on the left side you can see the average, the time average density map of water on top of a solid substrate. Now, at the temperature that we're using, you clearly see there's a sharp transition between the liquid phase and the gas, which in this case basically has even no molecules in the small simulation box. And this sharp transition is in a way preserved in the average picture that you see on the left at the contact with the surface. You see the high density red here, which corresponds to the location, say, of the oxygens of water at this level here. You see a second layer of water here where it's white, but at the liquid vapor interface, you just see a smooth decreasing density profile from the liquid to the vapor phase. Now, the width of this profile is also several times larger than the size of the molecule itself, which is in contrast with what we see on the right side, right, where the transition is really sharp. So the idea is to use some or develop some analysis tool that can allow us to really look at what is happening right at the molecular interface of these situations. I start with an example of a liquid-liquid, a system of a liquid mixture, water and carbon tetrachloride here on the right, and you see on the left density profile. The water density profile here in orange, and the carbon tetrachloride, which is an apolar molecule in red on the right. Again, there is a water molecule here roughly to scale to show you that the interface that we are seeing when we average with respect to the position of the center of mass of one of the two phases is actually broader than the molecule itself. This is not what we see in the snapshot, where I've highlighted the molecules at the boundaries between the two phases with this halos. Now, how can we improve this situation? The idea is simple. You can just place a reference frame instead of in the center of mass of one of the two phases. Use a locally changing one, which just sits on top of the interfacial molecules. We'll talk later about how to do that. But if you do that and you recompute the density profile, for example, but even other quantities with respect to this local reference frame, the picture you had before from the very same data changes dramatically. You see the structuring of water with a strong delta peak here at distance 0, which means molecules which are the interfacial water molecules one. And you see the strong structuring also of carbon tetrachloride, which basically behaves like a hard sphere with some attractive potential. Now, we can appreciate this way that locally there is much more structuring, and we can expect not only the statical structural properties to be very much dependent on the position or on which layer the molecule is sitting, but even the dynamical one. That's an example of several molecular liquids from the more polar one, water, to a polar one, which is again carbon tetrachloride, that interface with their own vapor. And you see that if you compute the diffusion of these molecules within the first liquid layer, and note that these molecules are never leaving the liquid phase, going into the gas and then back again. They always stay in the liquid phase. And the diffusion that you can measure in the layer, say in this case it's the polar direction, but the perpendicular works also fine, not going just into details, is basically for water as higher as twice of the bulk, value of the bulk, and in the extreme case of carbon tetrachloride, even 4 times higher in the bulk. And this has implication of the local properties of these liquids, of course. Now, all the analysis that you've seen here and that you see in the next slides are done with a series of tools that we collected in some Python suite that you can use to analyze basically any trajectory. Again, I'm not going very detailed in how these algorithms are working, but let's say just pictorially that you are, in this case, ideally rolling a probe sphere on the surface of the liquid, and just tagging as surface molecules one the molecules which are touched by this probe sphere. Of course, if you use probe sphere of different radius, you can get different set of interfacial molecules. And this was at the beginning a drawback, but basically we find out a way to give a thermodynamic meaning to all this. And we can show that we can find the optimal probe sphere radius for identifying the surface molecules such that within the surface molecules, the distribution here is the orange one with respect to the total one, which is in blue here, for example, for argon, such that with a given probe sphere radius, all the molecules which are within the liquid phase are has a border, this set, which is located exactly on average on the position of the equimolar Gibbs dividing surface. So basically, this set of molecules is the local equivalent of the macroscopic Gibbs dividing surface. So changing locally on the surface of the liquid. And this is an example of what you can do if you apply these methods to a problem of a shifting rolling droplet. Now this is just a movie from an actual MD simulation. We used not a spherical cap, but just a cylindrical one to avoid line tension problems. You see that we are able to apply this method both to the liquid vapor interface. You see these molecules are those tagged in blue. Those which I'm not showing here at the solid liquid interface. And the intersection between the two sets is basically giving you the molecules at the contact line, which you can follow instantaneously. You see the first layer of water molecules on the solid substrate here below, where you can clearly see the location of the molecules belonging to the contact line. Now, in this case, we are pulling the droplet, well, relatively fast. The capillary number is roughly 0.2, which is not too low. But at least for this time, it's not related to the fact that we cannot go low. We can, in fact, go lower in terms of capillary numbers, sampling long enough. There's no problem. But we wanted just to reach velocities such that we can see an effect of a combined rolling and sliding of this droplet and an asymmetric cap profile that you will see later on. So basically, the idea is the following. Once you have the surface atoms, you can compute the distance from the liquid vapor atoms and the distance of any molecules within the droplet and the distance of any molecule from the location of the interfacial atoms at the liquid solid interface. Once you have these two distances, we are making our histograms and then we are remapping them back into this two-dimensional map you're seeing now, which is the average profile or border of so the average location of the surface molecules. So we take this average and then we replot all these histograms in this reference frame, just for it to be a bit more easily understandable. And you see that basically where the border is here, this blue line is the equivalent of the delta peak you've seen before. This is the location of the first layer. Then you have the correlation shows you basically this deep blue area means that there are no molecules entering there because strong repulsion at the hardcore level. And then you see the layering at the solid, but also the layering at the vapor. And you can even notice the, say, interference pattern that grows here in the neighborhood of the contact line, which is located basically here where my mouse is now. So at the peak of the liquid vapor interfacial atoms and at the level of the first layer of water molecules on the solid substrate. If you zoom in the interesting part, you can appreciate how much information can this approach give you more than the usual averaging procedure in the center of mass of the droplet. And on the left is just a snapshot taken at a given time. This is not very representative, but you see where roughly the projection, say, on the vertical plane of the surface molecules and the contact line molecules are located. Should be roughly the same scale. Now we cannot just compute structural properties and density map, but we can also, sampling long enough as we did in this case, compute the average velocity field of this droplet. Now you see here that, I didn't mention this before, but this map is basically split in two, and you will see that there is a high level of uncertainty here in the middle. And this is because since your interface is fluctuating, the distance from of these inner points from the interface themselves, it's changing, right? So it's there that you're shifting all your sampling issues from the fluctuation at the surface. You shift everything to the bulk. But we are not interested in this region rather than in the interfacial one. So we are still happy about this. So you see that in this case, the droplet is sliding and also rolling on the surface. And basically you can zoom in again. This is the region of the contact line, as I was mentioning before, where you see the velocity field calculated in the center of mass reference frame, meaning that in the frame where the velocity of the center of mass of the droplet is 0. So this means that when you see an arrow here, which is very small, that part of the fluid is moving with a velocity which is the same as the center of mass of the droplet. Now, what we can learn here basically is that at the contact line, which is roughly located here, so where the first layer of water at the solid interface intersects the first liquid vapor layer of water molecules, the velocity at the contact line is basically zero in this reference frame, meaning that the molecules there are moving exactly at the velocity of the center of mass of the droplet, meaning that those molecules, if you want, are enjoying basically full slip in this sense. And then they are strongly braking whenever as soon as they enter and they pass the second correlation peak. Remember that the first one is the delta, and then you have a second correlation peak. And here they start decelerating, and their speed with respect to the solid substrate is decreasing. So basically, they are having a much
Marcello, excuse me, 2 minutes,
yes.
please.
We are done, so perfect. And let me just use this last slide to thank Amal, who's also in the audience, who did most of these simulations and analysis. And I just would like to present a teaser to our new research, which is on the motion of droplets on soft substrate. You see here a water droplet moving on a polymeric brush. And with this, I thank you for the attention.
Very much, Marcello. Very nice talk, inspiring, and very, very interesting. Thank you very much. Are there any questions from the audience?
Can I maybe just jump in here?
Of course.
That was a very interesting talk, and I was wondering if you'd thought about mapping these results that you have onto the lattice-Boltzmann or lattice gas kind of simulations that we've seen here. I mean, there's a lot of information here that would be very useful to map back there.
Yes. For lattice-Boltzmann, but not only, also for other CFD methods. For example, exactly the idea that locally you have your transport coefficient, like say a local viscosity or like local slit length that is really depending on the position. This is something that one might want to embed in more coarser description. Now, it also depends on which scale you are addressing with the different methods. Probably with lattice-Boltzmann it makes sense, because in a way to resolve properly the fluid, you need to go very low in also to need to have in fact a very high resolution if you want to match say the speed of sound in the viscosity of water. So I think there is good a good possibility of mapping back this to continuous methods.
Thank you, Alex. Other questions, please? Okay, if not, I would like you all to thank Marcello one more time, please. Thank you very much for this very nice talk. And we can go to have a very nice coffee. We have a 20-minute break for our coffee break, and then we come back here in the technical session number 5. Thank you very much. Thank you for these very interesting presentations, and see you in 20 minutes. Bye-bye. Okay. So it's 4 p.m. Good evening, everybody. We start our last session of today, technical session number 5. Before leaving, okay. Yes, thanks, Claudia, for the recording. I would like to draw your attention to the first, to the issue of the special issue of the last year of DSFD2020, which has been released by the Royal Society in the Philosophical Transactions of the Royal Society A. You will find all the details in the chat on the right and in the website. Okay, so in order to remain tight on our schedule, we go to our first speaker, Girotto, from the group of Professor Federico Toschi. He will present us droplets tracking in dense emulsions. Please, Ivan, you have 15 minutes. At 13 minutes, I will tell you that you have 2 minutes left.
Yes, thank you very much for the introduction. Thanks for the invitation. I'm actually an employee at the International Center of Theoretical Physics, and I just did recently this work in collaboration with Toschi that led to a PhD that actually was positively reviewed by Sauro Succi, who is here in the panel. So I will tell you a little bit about this experience, and which is about the design of methodology for tracking droplet in the solution. I will describe a little bit how we have reached three-dimensional high resolution the solution, the RCA computer simulation. I will talk about the method to track the droplets, to define and to try to quantitatively describe the dynamics of the emulsion during chaotic steering, and then I will show some of the results and drop some final conclusions. Emulsion are interesting physical systems because from two simple fluid via chaotic hydrodynamic steering, we can achieve a mix where one of the components is in the form of, say, a contiguous film, normally the component in the majority phase, while the component in minority phase normally assumes the morphology of spherical droplets. If like doing mayonnaise dome, we keep adding the component in the droplet phase, we can achieve a complex structure of, say, a mixed component that do not longer behave as a Newtonian fluid, but rather as a as an elastic solid, showing a characteristic of subglassy materials, such as, for example, the stress. Once the emulsion is formed, to avoid the two component go back to the initial stage when the steering is off, we need to add the surfactant, like in the case of mayonnaise, is the action of the egg yolk. The study of emulsions, in particular dense emulsion, is quite relative to industrial processes because include the number of product of food, cosmetica, paints, and as well as many other. However, the study of dense emulsions, the tail study of dense emulsion, is a scientific challenge due to the complexity of describing the system analytically. The challenge is to study them also experimentally due to the high concentration that prevent to accurately follow the dynamics of the components, making it difficult to uncover the dynamics and the rich physics phenomenology. And then also numerically, because this, the known models to numerical model to be able to represent this complex phenomena via computer simulation is considered very, very expensive, even as model space and time resolution. In particular, we look at this, we try to represent dense emulsion via computer simulation to try to answer, let's say, to contribute to answer to some big open question, like how to make this system look as real as possible, and then try to understand the connection of the multi-scale, like Francesca, for example, was presenting in the previous presentation, of the connection between the how the dynamic steering can impact on the small scale morphology of the emulsion, and on the other hand, how the composition of the emulsion can affect the flow when the system is exposed to hydrodynamic stresses. So we model this emulsion via Lattice-Boltzmann multi-component, modeling the fluid separation through, therefore, the surface tension through the Sansen-Chen model, and the disjoining pressure using which model the potential that avoided the mixing when the emulsion is at rest, using the model presented by Sbragaglia et al. And at the same time, we also apply, or let's say, simulate the model, the steering. So let's say we simulate the chaotic motion of the the system, the mixing basically, via the force field, which was introduced by Biferale and then used in other works from the group of Federico Toschi. The dynamic stresses is modeled via let's say sum of sine waves that are randomly evolved in time by means of a stochastic, to represent a stochastic process to ensure homogeneous isotropic state. So with these models running on supercomputers like the Marconi, hosted at Cineca, or the Mare Nostrum, hosted at Barcelona Supercomputing Center, we are able to achieve high resolution three-dimensional emulsion, dense emulsion, using a code that is being recently ported on GPU with a very say good performance in terms of let's say value for money and energy efficiency, such that we find the same time to solution using 8 nodes of Mare Nostrum compared with 1 node of Marconi, and our implementation includes let's say newly designed and highly efficient data structure for the lattice Boltzmann model. Capable, for example, here I'm showing that we were able to achieve 350 megabyte a second memory bandwidth on the kernel processor. So with these codes, we were able to create emulsion via interface fragmentation, as I'm showing in this animation, where starting from two fluids, because I'm referring mostly to binary emulsion, we break the interface and we form the droplet phase. Now, as I was saying, adiabatically adding the droplet component, we are able to achieve a very, very high dense emulsion, up to 77% of the volume occupied by the droplet in the system. Here, in this figure, I'm presenting the behavior of droplet in time, the number of droplets in time during a typical simulation, where you have that starting from a one droplet of the two component, we break the interface. Initially, we have an exponential growing of the number of droplets due to the fragmentation of the interface, and then when we keep pushing the volume fraction, the droplet gets bigger and bigger and smaller in number, up to a point when we stop the adiabatic addition of the droplet component, and we achieve a stabilized emulsion, still in chaotic motion, and then stopped and remains stable for eventually several millions of steps. With this methodology, we achieve dense emulsion at different volume fraction, because of course we can decide when we want to stop the adiabatic addition, and at different resolution we achieved up to 248 cubic resolution. We have seen how this dense emulsion present affinity and stress by applying a Kolmogorov test to different volume fraction. For example, here in the animation, I'm showing how for a fixed forcing amplitude, we see that the volume fraction flows quite vigorously, while the high volume fraction instead present only topological rearrangement similar to a plastic event. We have seen that we present here, I mean, the average velocity profile for the highest volume fraction at different amplitude of the applied forcing for the Kolmogorov test, and then here we show that for different volume fraction, different forcing amplitude of the Kolmogorov test, the system with high volume fraction of the dispersed phase show actually a finite value of yield stress fitting perfectly the Escher-Barkley relation as presented in this paper from Renzi et al. Now, to this code, we have added basically two algorithms to first identify and track the droplet during the dynamic motion. We identify the droplet first using this a very common algorithm of coloring based on the float field parallel algorithm, which is also presented in this reference here, and distinguishing the densities levels inside the let's say, the three-dimensional system or the three-dimensional density field, we can identify every single droplet by distinguishing which is the level of density inside and outside the droplet, such that we can basically, for a given time step, fully decompose and reconstruct the entire system droplet by droplet. However, okay, this identification of droplet allows us to create very large, let's say, very accurate statistics over a very large number of samples. For example, here I'm presenting the droplet size distribution of the droplet in time for different time frame of the simulation, starting from the top left to the bottom right. So here we have where the interface is broken. Actually, this is quite interesting because it shows a slope of the droplet distribution equal to the -10 to the 3, which is being normally attributed to a droplet in turbulent motion, while here we are basically almost laminar. But when we break the interface, the chaotic motion of the interface gives this kind of droplet distribution. Then, while keeping the simulation and keeping with the pushing, we see that the droplet size distribution change, assuming a very wide extension of droplet range. And then finally, when the volume fraction becomes higher and higher, we start to notice this bimodal distribution with the peak of the average radius much higher than it was for lower volume fraction, meaning that the droplets are growing in size, but also with the presence of a large number, or say a relevant number of small droplets. So to add value to our analysis, we also introduce a tracking algorithm that allow to not only identify the droplet, but to follow them in time, basically being able to reconstruct the Lagrangian profile of the droplets in chaotic motion based on let's say a probability transition that define, given two time step, that define the probability that one droplet exists at the following time step. If the droplet doesn't exist, we check either if the droplet, let's say, is part of a phenomenon of breakup, meaning that at the next time step there will be two droplets that are equal to the volume of a droplet at the previous time step, or a phenomenon of coalescence, where it means that two droplets at the time step T1 are equal to the volume of one droplet at the following time step. So implementing this algorithm in our code, we are able now to identify all the event of breakup or coalescence during motion. And we can see here, for example, these are preliminary results of the analysis. We can see that given a constant forcing, for example, here on the top, given a constant forcing by varying the volume fraction, you can see that for lower volume fraction, there is basically no dynamic for low forcing, while for high volume fraction, we start to see a significant number of events of both breakup and coalescence. On the bottom side, instead, I'm showing the difference between the same system where we apply different forcing amplitude, and we can.
Sorry, 2 minutes, please.
Yes. For higher forcing amplitude, the number of events increase rapidly. Now, with this, we can also show a PDF of the droplet size distribution connected to the number of events. The same way, we can also show how is the probability of the event in function of the droplet size. We can reconstruct Lagrangian profile, as I'm showing here on the left, where I'm showing the trajectories of droplet for 2 million steps during simulation. And here on the right, I'm showing instead a PDF of acceleration, which shows a profile fitting the stretch exponential that other works have found for, experimental works have found for a droplet in turbulent flow. Of course, okay, these are other results showing that if we put the acceleration, the the radius in function of the acceleration. We see that for higher volume fraction, the higher acceleration is given by the small droplet that eventually have some effect of intermittency inside the bigger droplets. Here are the conclusions. So basically, just to conclude, we have implemented a model that allows to investigate the solution in mesoscopic scale. We designed a new algorithm that combined with the color algorithm allow us to track the droplet in the solution during motion with quite good accuracy. And we have generated a very large number of statistics that we are that we are starting to analyze in these days. Here are really preliminary results that will be further published. And then, of course, this allow us, however, have demonstrated that allow us to analyze the behavior of the small scale in function of the aerodynamic steering and the behavior of the aerodynamic steering flow in consequence of the droplet of the emulsion morphology. Here are the other persons that contributed to this work, and here is the final acknowledgement. Thank you very much for the attention. Sorry for the mute off.
No, it's fine. It's fine. Thank you, Ivan Girotto, for this very interesting presentation and talk. Are there any questions from the audience?
One, if possible.
Yeah, sure.
Yes, please.
Yes.
Ciao, Matteo.
Hello, ciao. So just one question. I dealt with basically the same problem a few years ago, but in 2 dimensions. Now, I just wanted to ask you why you use a probabilistic approach, in the sense that, in my case, maybe because the algorithm was less computationally intensive to assign a label to each droplet, we could basically run the algorithm, say, every 100 time steps.
Yes.
So tracking the droplet was pretty easy, because once you have the label, basically you just keep on following the label one way or another. You just minimize the distance between droplets and you can associate them. Is it you resort to a probabilistic paradigm algorithm because you want to have large time separation between trackings?
Absolutely. We wanted to, sorry, have you finished the question?
No, in the sense that, no, yeah, more or less on this. Please go ahead. Then if I...
Yes, it's the fact that we want to have different, we want to measure the accuracy of, we haven't done it yet, but we want to measure the accuracy of the algorithm, different time, with different time frame between one screenshot and the other one. But especially this is also because we expect that when we increase the forcing, and of course, we can do this only for less dense emulsion, but this idea is also to track droplet in general. The droplet deformation would be quite substantial, so it becomes difficult to identify like one droplet. In every time step, okay, in every time step that we screenshot, we have different number of droplets, and we cannot keep like track of one droplet from one time step to another. How do we do that?
No, I did.
Yeah, and how did you do it?
Exactly as you say. You keep on minimizing the distance between the relative centers of mass from one snapshot to the other, and that provides you the unique mapping of the labels from one snapshot to the other. The biggest difference that I see between is just to understand the reasoning, because you just presented the method without exactly, of course I understand, but I just wanted to ask you more in detail the reasons why. The clear differences for me is that you're working in 3D, and so doing the tracking might be more computationally intensive than what I've done, because it was only 2D. So that also can explain. I just wanted to understand more about this. What is the smallest time step that you have tried to track?
The smallest is, we can also track one, but let's say normally to keep this sustainable, we have to
exactly
every 500 time step, something like that, 500, 400, even more.
But then, okay, but then it should be, you're not working at such high Mach numbers. So in a sense, you should be able.
No, for these scales, for this kind of forcing, I think it should be able. But we definitely wanted to think it as something that would have been we could have used a different really amplitude forcing, so different velocity, where we expect the motion to be much, I mean, way farther.
It's more like a particle tracking.
Yes, exactly. Yeah.
Okay.
Exactly.
Okay.
Yes.
Thank you very much.
Okay. Thank you very much. Thank you, Ivan, one more time for your very nice talk.
Thank you all.
And we can move to the other speaker, Guskova. Are you online?
Yes.
Okay. I cannot, Maria, I cannot see you. Please, Ivan, you can stop sharing your screen, please.
Yes, excuse me.
No problem at all. Please, Maria, can you try to share your screen, please?
Yes.
Okay, okay.
Do you see?
Yes, we see very well. Now, please, you have 15 minutes. At 13 minutes from now, I will tell you that you have just 2 minutes left. Okay? Please, the floor is yours.
Hello, I am a PhD student at HSU University in Moscow, and today I will talk about lattice-Boltzmann method simulation of the chain of the drops. So the problem is quite common for microfluidic devices, and there are two large sets of laboratory experiments on the chain of drops or a bubble flowing in the narrow channel. So the interesting phenomena can be observed. For example, some periodical structures appears, such as transversal or longitudinal oscillation in the 1D array of the drops. And the second experiment lies in the biology section, and there are several collective motion effects in the motion of the cells and the cluster of the cells in the blood. So in the mentioned paper, there are transversal and longitudinal oscillation observed, and they are explained by dipolar long-range interaction. So if we have 3 particles placed antisymmetrical, then the middle one wants to move upward because the forces from the left and from the right particle are pushing it upward. So there are not only transversal oscillation, but the longitudinal too, and we are going to build the computational step to investigate the reasons and the interdependencies in such situations. So our first part will be about one drop oscillation and the oscillation of one drop in the chain of 3 drops. It was done using Shantian model for multi-component flows. And the second part is about the motion of rigid disks in Poiseuille flow. So I'm using a lattice-Boltzmann method. There we're solving the lattice-Boltzmann equation. Sorry, so I will not stop here because I think everyone is acquainted with this method. So I use the Palabas software. It has already implemented lattice-Boltzmann, Shantian, and the Immersed boundary method, and also all the parallelization works handled by Palabas and the MPI processes. Shantian, my first problem is about one drop oscillation. So I have 2 fluids, one of the drop and the other is environment. And then I have 2 lattices and for each of them, Lattice-Boltzmann is solved, and the interaction between fluids is carried by additional source term Si. In the initial step, the drop is elongated along that axis, and also the computational domain is the box. So after the simulation is started, the drop oscillates, and the frequency is defined by analytical relays formula. Here, n, the agent mode of oscillation, is equal to 2, and from the formula, we can see that the squared frequency depends on cubic inversed radius as linearly. So we've checked for 2 viscosities and found out that the formula is fulfilled. We have, and also that the ratio of the slopes of the lines is the same as the ratio of the viscosities. This second experiment, I have a chain of 3 drops. The middle one is excited as in previous experiment, and after it starts to oscillate, after some time, the side drops moving towards the walls. And it happens for all of the viscosities we've checked, but different times. So some of the effects in the chain of the drops can be caused by internal, by the oscillation of the drops. We just checked that this happens in all cases. For the last part, we've used immersed boundary method and represented drops as rigid disks. For each disk, we can determine the force which is acting from fluid to the particle, and then just integrate the classical Newton's laws for every particle by implicit Euler method to move it on to the next time step. So we placed an array of rigid disks on the central line, and the central particle is lifted by the quarter of radius. Also, the length of the chain is about 1,000 times less than the length of the cylinder of the channel. And Poiseuille flow is set everywhere. We've checked for the 3 different sizes. They differs in the linear sizes. Also tried a different number of particles, and there is no dipolar interaction, as we consider truly 2D problem. Particles are moving at approximately the same velocity as the flow does. So, but in the physical experiment, the drops of the water are 5 times slower than the flow, and because of the friction of top and bottom walls. So that's important because we do not have dipolar interaction, but we have seen the oscillation too, not the longitudinal one, because on this picture the distances between neighboring particles is shown. So this, for example, this line is distance between the first particle and the 0 particle. we can see no longitudinal oscillation, but for the y coordinate, there are oscillations, and Fourier transform in space and time shows this spectrum. The first line is for longitudinal oscillations, and the second line for transversal. On the right column, you can see the results from the physical experiments from Vitus article. And, they have like very small Reynolds number and a bigger number of drops. So we can see we cannot observe any longitudinal oscillation, but the transversal, which are caused by the reflected waves, more visible for the narrow channel. So to conclude, I would like to say that we've checked Rayleigh formula, and the frequency of the oscillation of one drop is followed it, and the secondly, excitation of one drop in the chain of three another influence the neighboring drops. And also we can say that transversal oscillation in the chain are partially caused by the reflected waves. At the same time, longitudinal one caused by dipolar long-range interaction that I can say not only from the lattice-Boltzmann simulation, but from the results of the integration of ordinary differential equation, in which equation were built only on a theory of dipolar interaction. Thank you for your attention.
Thank you very much, Maria. Are there any questions from the audience? Actually, from myself, just a comment. Maybe you could also resort in the future to derivations from the Shanchen equation of state. For instance, the double belt, in which you can consider the presence of repulsive tails and see the behavior of the droplets in the presence of such repulsive forces, instead of only the presence of the Shanchen action.
Okay, thank you.
I sort of looked at your feedback on the personal statement, and that, you know, that last sentence you were writing really struck me as like a good bit of writing, you know. But I really feel like I understand that my statement right now in its current state is very weak, and I don't feel like I actually can replicate the quality of the standard of writing. I'd like to sit down and sort of, yeah, sure, we can work.
Okay. Professor Lowe, we were hearing you. If there is any question. Okay. Are there any other questions from the audience? Okay. So what about me once more, please, Maria, if possible. What about if you can go back to the slide in which you show the three droplets with the different behaviors. Okay, the chain of three droplets. Okay, yes, the number 11. Okay, okay. So what about, or for this one. Okay. What about the boundary conditions? Which boundary condition did you implement? No slip boundary conditions?
Yes, I have bounce back, no slip boundary condition. Bounce back, no slip boundary condition.
Okay. Okay. Just a curiosity. Aren't the walls a little bit too close to the droplets? Don't you feel that there is a confinement phenomena that can take place in this domain?
I haven't checked that. That's an interesting question.
Okay.
Confinement, in which direction? Because I
Boundaries
have,
that are too close.
yes, they are closed. Okay, I will check.
Okay, okay. Just in the future, just to you can, for instance, make sure that doubling the dimensions, you retrieve the very same results, so that they are grid independent. We say, okay, with the same dimension of the droplets, you enlarge the computational domain, making the walls farther away, more distant from the droplets, in order to check if they have any influence. Okay. Okay, so if there are no other questions, I would like to thank Maria one more time.
Thank you.
And we can go to our last speaker of today. We have still a couple of minutes. If you would like to, Raymond, good evening. If you would like to share your screen and let us hear you. Can you hear me?
Yes, I can hear you. Right.
Okay. Okay.
Yes, I can hear you.
Yes. Okay. That's fine. No, I didn't hear you before. So let's wait just a couple of minutes for the other attendees in case to join us.
Is
then
my voice too loud?
We
or
can start our presentation.
Is my voice too loud? Or
sorry, excuse me?
Is my voice too loud?
Giacomo, there is a strong
voice
return of audio from the speaker. Strong return of audio from the speaker.
Well, I don't hear it.
Right, let me try to reduce my my speaker. Let me try to reduce my speaker gain.
Yes, just speaker volume maybe.
Right, so I have reduced it. Is it still too loud, or is it? Right, so I have reduced it. Is it still too loud, or is it?
No, it's fine. It's fine.
All right then. Right. So.
Okay. So let's wait just another few seconds. Okay. So our last speaker of today is Raymond Cristianto from the Department of Physics of Durham University, and he will talk us about the modeling of droplet dynamics on a fiber. Please, Raymond, the floor is yours. You have 15 minutes from now. When you will be at 13 minutes, I will tell you that you have just 2 minutes left. Okay?
Right.
Thank you very much.
Right. Good afternoon, everyone. Thank you for your kind attention. So welcome to my talk this afternoon. Today I'm going to talk about my work, which is modeling droplet dynamics on a fiber. Right. So manipulation of droplet dynamics on fiber is very important for a lot of problems. So one of the most common is if you have a wire mesh, and then you want to use it as a fog harvester. Then after the condensation, you have to transport the droplet, and then you are going to collect it. If the transport is not done correctly, then the mesh structure can be clogged, which means that the efficiency of the structure will be reduced, and then you cannot use it to collect water anymore. Another case is that if you have a fiber junction, like this work by Weir et al., you can create, if you have a different fiber radius of fiber junction, like in this case, it has a thicker fiber horizontally and then a thinner vertically. you can actually create a compound droplets, which means you have a smaller droplets with a couple of smaller droplets encapsulated by larger droplets, and then it can be transported somewhere else. Or if you have array of fiber junctions, like source picture number 4, you can see that it can be directed to a certain direction or certain position by using the fiber junction. So in the past, there has been a lot of research on the relation between droplet velocity and external force. Usually it has been done on flat surface, on rough or smooth surface, or conical fiber or cylindrical fiber. But usually it's been done for fiber, usually it's been done for fully wetting condition. And they also found that usually the relation between the velocity and external force is linear. But at high velocity, this relation will break down, and then the droplet can actually adopt different shapes. For example, on the strike picture, you can see that at first it stays rounded. It can then later develop a corner at the back, and then can pour or really smaller droplets from the tail. So in my work, I'm focusing on a dynamics of the droplet on a partially wet fiber, which means that the fiber has a certain contact angle. And then I'm focusing both on the barrel and clamshell configuration. I'm going to explain what's the difference later. So I'm not going to talk in details about the tools because it's already quite well known. So my main tool is the enterprise displacement, which has been developed by Ilya Karlin. My advantage of using the enterprise displacement is that I can simulate a high density ratio system, which means like a water with air. And then the equation of state we are using is the Karnan-Starling EOS, which advantage is based on a real fluid. The fluid-solid interaction is modeled using the forcing method. We are using this, so this is not the most accurate, but because we are having a complex surface, we approximate the curvature of the cylinder by using the staircase approximation, and then forcing method is one of the easiest way to implement this. The velocity set is PQ319. We ignore the hysteresis, the contact angle hysteresis effect. Related to the physical parameters, we use the bond number and capillary number. The bond number compares the gravitational and surface tension, while the capillary number compares the viscous and capillary effect. One particular note here is the relevant length scale is actually omega per RV, unless noted. So we are using omega per RV instead of like T squared or R squared, because in general we try to include the effect of fiber diameter or fiber radius to the bond number. So to gather all of the data to find the scaling law, we try to include the different fiber radius. So that's the number of bond number and capillary number. It's generally equivalent to a millimeter or 100 micron size droplets. So first we have barrel configuration. So one key characteristic of barrel configuration is when you see it from the side, like this, the right figures, bottom right figures, you can see that it's actually axisymmetric. It encapsulates the fiber. And then we choose 3 different contact angles: 28 degree, 60 degree, and 75 degree. As you can see, by changing the contact angle, we can see the change in the length along the fiber, or we call them W here, and the height of the droplet, which we call X. X doesn't change significantly. W seems to be more moving, can change quite easier, which it makes sense because the droplet is confined that it has to encapsulate the fiber. So increasing contact angle makes it less wetting, means that we actually reduce the W, the length in alongside the fiber or the W. Then what we done is we done a lot of different droplet volume, and then we calculate the capillary number, the bond number. We convert them to we calculate the log of capillary number and bond number, and then we fit them linearly. We have 2 figures here. On the top is just CA versus bond number, while on the bottom we have capillary number versus W over X times bond number. So the reason why we are using W over X times bond number is because in the past, for a fully wetting condition on a conical and spherical fiber, the scaling law has this aspect ratio part, or this W over X. And to our surprise, when we did it for a partially wetting for 28, 60, 75 degree, by including this W over X ratio, the graph collapsed into one single line, or we have the scaling law, which is very similar to what has been done on a fully wetting fiber. The relation is linear, as you can see on the table on the bottom left. The M, or the slope, is almost 1. And if you see the constant, which is A, with W over X, the difference between each contact angle is not as pronounced as when we don't include the W over X prefactor. So what if we go to clamshell configuration? So compared to barrel configuration, clamshell configuration is not axisymmetric. The droplet just like perches on the fiber. And then if we change the contact angle from 60, 75, and 120 degree, we found that now the droplet can move more easier, which means the difference in W and X is more pronounced. As you can see, for example, on the side view, the YK, ZK, if you have 60 degree, it will stay. The right side will stick to almost at the bottom of the fiber, not encapsulating, but still quite a lot. But if you have 120 degree, the droplet will move to the top and will not try to wet as much as possible. This means that the contact area change is now more significant compared to the barrel configuration. Again, we calculate the coupler number, the bond number, compare them with and without W over X. We found that for clamshell configuration, that the prefactor does not collapse the graph, which means that it behaves quite different compared to the barrel configuration. However, the fitted line is still linear, and as you can see, the constant is now, so the difference in contact angle also pronounced the difference in constant more significantly. I mean, basically, the difference in constant is now more pronounced because even though when we have different contact angle. And then if we compare the clamshell to barrel, first we can see that clamshell is certainly faster. So for the same contact angle, both green and orange, if we in clamshell, then at block bond number -6, it actually intercept about between -10 to maybe -9.5 or something. While for barrel configuration, for the same contact angle, for same green and orange, it is closer to -11, which means that clamshell is certainly faster. And then the difference in contact angle is more pronounced in clamshell than barrel. As you can see, the separation between the contact angle is much more clear when we have a clamshell configuration. So now we are most of the time we just talk about quite a low bond number, which characteristic means that the droplet shape doesn't change significantly; it still stays rounded. But when we're working on it with higher bond number, we found something interesting. So what we did was, okay, let's do a systematic effect. Let's do a systematic test. Varies the fiber radius from 10 to 40, and also do a simulation on a flat surface for benchmarking. Fix the droplet volume, fix the contact angle, and then here we change the definition of bond number from omega over RF to omega to the power of 2 per third. Basically, we're saying that the length scale is the cubic root of the volume. It doesn't matter which kind of length scale you want to use. You can use d squared, the real square diameter if you want. But yeah, this is just the way we did it. So here we have a phase diagram. On x-axis is the length scale divided by the fiber radius. On the y-axis, you have this new bond number definition. It varies from 0.6 to about 2.8. This parameter is equivalent to a water droplet with radius about 4 to 8 millimeter. So we found at least 3 different cases. We categorize them into 3. So it's circle, star, and square. Circle means that the droplet will stay intact. Stays intact means that if we run it for a long time, the droplet will not separate into 2 or will not separate into 2 or more satellite droplets. If the bond number is quite small, the shape will be more or less still symmetric. You can clearly see that it starts to develop a tail at the back. But it's not that pronounced like the middle one, where you can see the back part is very sharp and then the front part is very rounded. Or we can also find a more extreme case where it starts to develop a tail at the back, but it's still not separated even if we run it for a long time. On the second case, then the droplet can break up. We categorize, we try to see them into two like cases. First is when we have a short tail. So if you can see here, it start to move, it separates into two, and then you have a short tail. It also releases one satellite, not quite, not very large, but it's quite large compared to a more small, a much smaller the satellite droplets. Well, on the other case, we can also find that it will develop a quite long filament with quite large satellite droplets. And usually happen when we have a quite high bond number. We also found a middle case where the droplet actually oscillates. So oscillates means that it actually develops a long tail or a short tail. You can clearly see the front and the back part, but the filament will not break up and instead will retract. And then it will either keep doing extension and retraction, or will do one extension, one retraction, and then just moving around like that. So in general, for a flat surface, we found that increasing the external force or increasing the bond number, we will increase the stretching until a certain point it will break up. As you can see, it stays rounded, start to see like corner-like shape, and then start to develop tail. So with our current model, we actually cannot find any breakup, even though we push the bond number to about 4 times of the maximum, which is already at the limit of our code. We still cannot think. We cannot see any breakup. We can just see a very long tail, very thin, very long tail. I already said before that we are using the forcing method. It's not the most accurate, but it's much easier to implement for a more complex geometry. We try to use a much more accurate model, but at the end of the day, it's still the same result. It's still we have the same. So it's probably physics. And one thing we already mentioned is that we don't have any contact angle hysteresis effect, which means that that's probably the cause. But what we want to suggest is actually, instead of playing with the hysteresis or the roughness of the surface, you can actually just introduce a curvature. So if you have a fiber, as you can see, comparing these two, for the same amount of force, the same amount of bond number, with a fiber, you start to see much more, you see a longer tail. The droplet shapes are much more distorted. And then if you keep increasing the curvature, you keep decreasing the fiber radius, you start to see breakup. And then the minimum force needed to induce the breakup also been reduced. The bond number is getting lower and lower. Pardon me. Right. So during this intake phase, the transition is...
Minutes, Raymond, please. Thank you very much.
No problem. Right, so during intake phase, the transition continues, which means it will start to develop a tail. But then after a certain length, it will start to break up into two. So it's quite abrupt. But then between the short filament to long filament, the transition is very continuous. So in conclusion, the manipulation of droplet dynamics is very important. It has been used in different cases. For low bond number, the relation for barrel and clamshell is linear. Barrel configuration for a partial wetting condition behave quite similar to the fully wetting condition, but it's very different for a clamshell configuration. At high bond number, this linear relation will break down. The droplet can adopt different shapes. We actually see intact, breakup, and oscillation. And this breakup behavior can actually be induced by introducing a fiber curvature. So we are currently doing a couple more works regarding this topic. So first, we are quite interested with the filament length, and then the droplet volume at the back actually increase with increasing the force. But is there any different kind of trend? So far, what we can see is that for different fiber radius, if you keep increasing the force, the length, filament length will increase significantly. So from the bottom to the middle, but later it will plateau, or even then in some cases it will be reduced. We are currently working on this. We are also working on one more topic, which is during the breakup for flat surface, what has been commonly seen is that it will pour or really small satellite droplets in a constant rate, or maybe not so constant. But what we can see is that actually, in most cases, it will release a slightly larger before it releases much smaller satellite droplets. And then is there actually two breakup mechanism happening at the same time or competing, breakup versus purling? And then we are working to identify this. Currently, one approach we are using is using the Girotto tensor to identify the breakup pattern. So this is the very early works. So that's my presentation. Thank you very much for watching. I will happily answer any question if you have.
Thank you very much, Raymond, for your nice talk. Are there any questions from the audience?
Right, so I saw a question from Andre, I guess. On your plot,
yes,
of the
Andre, on your plot of the rounded to purling, you see that for some radius and bond number, the droplet breaks, but if you increase the bond, the droplet oscillates. Any idea why?
Yeah, so this is actually, we have actually investigated this part. So far, our conclusion is this particular value. So at 3.09 third column and then at 2.830 for the bond number, this is actually a reentrance, because if we keep pushing them higher, we actually got the oscillation back. So we actually haven't really found the explanation why this happens. But as far as we know, that if we continue, we add two more bond number for 30 and for this two column, we actually see more oscillation. But then we're still not sure why at this particular point we see the breakup. We think that there is some kind of competition between the inertia, so between the elongation by the inertia and then the retraction by the surface tension, but we haven't really delved deep into this question. But yeah, thank you for your question.
Can you hear me?
Yes, I can hear you now.
Sorry, excuse me, my microphone was off. Isn't it related to the Weber number? No.
The Weber number.
Because the transition, the breakup for ligaments and droplets and so on is also studied with the Weber number, which is rho U square D over sigma with the
yes.
characteristic length.
Yes.
And maybe this transition from rounded to purling, we have simulated this in another work for the breakup in liquid ligaments.
Right.
Maybe the explanation may be related to the different value of the Weber number there. So this behavior can be different as Andre Matthias was saying. Okay.
I see.
It could be worth investigating the values of the Weber number. Okay.
Yep. Yeah. That's a very good suggestion.
Let me know. Maybe it's just a thought on 2 feet. So let me know if this is fair. Okay.
Yeah. Yep. Thank you. Thank you.
Okay. You're very welcome. So let's thank Raymond one more time. And I would like to thank you all speakers and attendees. This afternoon session was very interesting. And I wait for all of you tomorrow for our morning session of Wednesday here in Sala Leone, Room Leone, with the plenary talk by my friend and colleague Tim Kruger. And I really hope you are enjoying, like me, this DSFD21, because I find very, very interesting and inspiring all the talks. So thank you for attending this afternoon session, and have a good night. Bye bye, you all. Thank you very much.